29th of May, 1660. A tumultuous welcome from the people of London. King Charles II's return from exile and the restoration of the monarchy. This was also the start of a new era of English scientific and mathematical research. For now, an organization could be formed for the promotion of the physico-mathematical experimental learning. The Royal Society was soon granted its Royal Charter, but to appreciate its significance and aims, we need to go back 60 years to the start of the century. Sir Francis Bacon and other intellectuals were greatly concerned by the state of learning at that time. They felt that it was being hindered by the traditional philosophies as taught by the universities. These philosophies were based on a system of logic expounded by Aristotle, by which assumptions are made, and from these assumptions, conclusions are drawn. Bacon argued that if the original assumptions were at fault, then the deductions must be unsatisfactory. However, the state of academic learning was such that long-held assumptions were not being questioned. Bacon instead proposed a radical plan of work, his Instauratio Magna, by which it would equip the scientist to pass, he said, beyond the confines of classical science. Thus, the ship in his frontispiece passed through the Pillars of Hercules into the uncharted regions ahead. The foundation of Bacon's plan is what he calls the natural history. This represents the facts of nature, from which the new science would be formed. Bacon outlined a program of scientific observation and experiment to obtain the basic incontestable facts upon which all else would depend. In his New Atlantis, written in 1626, Bacon envisaged a scientific college, Salomon's House. Here were laboratories and instruments, and observers and experimenters, and others to draw from this work and formulate nature's laws. The New Atlantis and Bacon's other writings aroused great interest among the learned. But could Salomon's House be realized? However, even before this, a merchant, Sir Thomas Gresham, had been deeply concerned by the poor state of adult education in London. He left a substantial sum of money to set up a college. In 1598, Gresham College opened to the public. Here, citizens could attend lectures on a range of arts and sciences, including geometry and astronomy. It was above all designed to introduce practical applications of mathematics. Henry Briggs, professor of geometry, was the first to popularize the use of logarithms. These replaced the task of multiplying two numbers by the much simpler task of adding two other numbers. The inventor of logarithms was a Scotsman, John Napier. Napier thought of two lines, one of finite length, the other stretching away to infinity. Now he considered 2 points, P and L. They both start moving at the same speed, and L just keeps on going at that speed. P, however, is slowing down. Its speed is equal to the distance it still has to go, its distance from the point Q. So when it's halfway between P0 and Q, it's only going at half its original speed. Now for the definition. Freeze the action. The distance L has traveled is called the logarithm of the distance P has yet to go. Napier produced tables of logarithms of numbers using this model. Here's what you had to do to multiply two numbers together. You take the logarithm of the first number, add the logarithm of the second, then subtract the logarithm of the number 1. Then reading back from the tables, you get the product. However, it was awkward to subtract the logarithm of 1 in all the calculations. Henry Briggs simplified the problem by improving the definition of logarithms. Now, the logarithm of the product could be obtained simply by adding the logarithms of the individual numbers. And in this way, he popularized the use of logarithms for tradesmen, craftsmen, and seamen. And these are the tables which Henry Briggs compiled and promoted at Gresham College, calculated with great precision to 14 decimal places. The use of logarithms was soon made more simple by incorporating them in an instrument. Alan Chapman takes up the story at the National Maritime Museum.
When Edmund Gunter became Gresham Professor between the years 1619 and 1626, he did a great deal to popularize the use of logarithms and other devices for mathematicians, astronomers, and navigators. One of the key things which he developed was an instrument which came to be known as the Gunter scale or the Gunter sector. It was indeed an early precursor of the modern slide rule and allowed one to make elaborate mathematical calculations. I'm going to demonstrate a simple example, the multiplication of the number 2 by the number 3. One required a pair of compasses or dividers to make the calculation. All that one required to do was to first of all strike off the number 2 on the scale. 2 3s are 6.
During the 1630s and 40s, the professors of Gresham College continued their program of teaching and made great advances in applying mathematics to problems of navigation and surveying. Gresham College was not the Salomon's house of Francis Bacon, but some of its professors and other science lovers were becoming interested in the new philosophy. John Wallis later recalled meetings in London. About the year 1645, we did meet weekly, sometimes in Wood Street, sometimes at Gresham College. Our business was to consider of philosophical inquiries, as anatomy, geometry, astronomy, navigation, statics, magnetics, mechanics, and natural experiments. But England was in turmoil. The Civil War was raging, with Oliver Cromwell holding the southeast of England. In June 1645, the Parliamentarian army won the Midlands at the Battle of Naseby, and 1 year later captured the final royalist stronghold at Oxford. With Cromwell now in full control, known royalist sympathizers were ousted from the universities of Oxford and Cambridge. Several members of the group meeting at Gresham College were appointed in their place. John Wallis was appointed Savilian Professor of Geometry at Oxford, and John Wilkins, Warden of Wadham College. Under Wilkins' leadership, the college quickly gained a reputation for freedom of thought. The philosophers who had moved from London now met weekly in Wadham College, joined by others who were interested in the new philosophy. In 1651, the members of the informal weekly gatherings formed the Philosophical Society of Oxford. It would soon include many who were later founders of the Royal Society. Robert Boyle was a member, as were Thomas Sprat, the first historian of the Royal Society, and Henry Oldenburg, its first secretary. Christopher Wren also attended the meetings and studied mathematics at Wadham. In 1663, Wren was entrusted with his second architectural commission, the Sheldonian Theatre, Oxford University's principal assembly room. His ability to do mathematical calculations was qualification enough for him to take on an architectural contract. Wren chose to design his assembly room in the style of a Roman theatre. But the open-air theatre of ancient Rome was not practical in Oxford. Wren was able to design this completely flat roof, totally without supporting columns. But to achieve this, he had to solve the problem of suspending the flat ceiling. Fortunately, Wren was able to look back to his student years at Wadham College for inspiration. For John Wallis had addressed this very problem in the 1650s. He had constructed a model and also calculated its load-bearing capacity. This was most ingenious. The length and breadth is much greater than any of the individual beams, and it is totally self-supporting except at its edges. So, at the center, we have 4 beams, each supporting one of the others at one end. The other ends are supported by further beams. These are then supported at the ends by others, and so on, until the edges are reached. He recognized the symmetry, and he labeled all 4 corners of the central square A, both to refer to position and the weight that the supporting beam carries at that joint. Other joints were labeled accordingly. Then, to calculate the weight on this joint A, he realized that this is made up of 3 components: a proportion of the weight of the beam lying between A and B, a proportion of the weight at this other point labeled A, and a proportion of the weight at C. Now the weight of the beam AB he sets equal to T. The weight supported at this point A is just A. At the point C is just C. Now he needed to work out the proportions of these weights acting at the upper end of the beam AB. He arrived at this. Adding these up and setting them equal to A, the unknown weight at the top of the beam AB, he gets this equation. In a similar way, he derived equations for every other joint in the model. He then solved all these simultaneous equations to give a value for the weight on each joint as a multiple of T, the weight of an individual beam. Since the architect would know what weight each beam could safely carry, he now knows whether the construction is safe. This was an ingenious piece of applied practical mathematics, combining the mechanics of levers and the algebra of simultaneous equations. In his design for the flat roof of the Sheldonian Theatre, Christopher Wren was able to call on these principles and adapt them. Wren also had the benefit of being able to use supporting trusses in the attic space. Indeed, the roof support was so strong that for many years this attic was used for storing books from the university press. In celebration of the new philosophy, the ceiling depicts the triumph of the arts and sciences over envy, rapine, and brutish scoffing ignorance. The mathematical sciences are represented here. Optic, with the telescope, arithmetic, geography, and geometry with a pair of compasses, astronomy, finally, architecture, seated by a workman holding a plumb line. Towards the end of Cromwell's rule, Christopher Wren and others from the Oxford Philosophical Society were gravitating back towards London to rejoin the group of philosophers meeting at Gresham College. Wren himself was appointed Professor of Astronomy. With the restoration of the monarchy, they could consider forming a society on the lines of Bacon's principles and with the approval of the King. Here is the record of the first meeting of the Royal Society in November 1660. But how did the members promote the new philosophy?
Having a formally organised society did bring a number of benefits. Firstly, it acted as a focus for all scientific minds in the country, and here all those interested in scientific investigations could report their findings and listen to the observations of others. Beginning in 1665, Henry Oldenburg, the secretary of the Society, published his monthly Philosophical Transactions, the oldest scientific journal in the world. And here for the first time was a means of mass producing the results of scientific research. These philosophical transactions could be and were distributed widely throughout Europe and had great influence.
Looking at these early issues, you notice a number of differences from a modern scientific journal. The non-mathematical articles were written in a very plain English. Experimental science had not yet developed its massive jargon and procedures. But it's worth noting that mathematical treatises still tended to be written in Latin, the language of the trained scholar. And there were many articles dealing with unusual phenomena, rare objects, or just hearsay. It was easy, then and now, to ridicule many of these articles. It's only from our 20th century viewpoint that we perceive some articles and observations as of greater consequence than others. To the 17th century experimental philosopher, all facts were of interest. One topic discussed at length over a number of articles concerns the nature and behavior of light. It exemplifies the role of the Royal Society. In the Philosophical Transactions of 1672, there appeared the first correspondence from Isaac Newton about the development of his investigations into light and colour.
That article and the ensuing debate in the Philosophical Transactions probably did more to advance scientific knowledge of optics than had anything before. And indeed, this series of experiments, observations and formulation of laws was seen by many as a prime example of Baconian principles at work. And only 4 years later, the Royal Society was involved in the setting up of a most ambitious project in experimental and applied mathematics to date. One whose aim was to solve a long-standing navigational problem and which would lead to a golden age in British astronomical observation.
One of the major problems for the 17th century mariner was that of determining the ship's position at sea. Pilot books had been available since the 15th century. But once the navigator was out of sight of land, with no familiar landmarks, what did he do then? A convenient way of defining position had been in use for centuries. Latitude is defined as degrees of arc above or below the equator. Calculation of latitude was fairly simple. The pole star, positioned almost directly over the North Pole, was a reliable indicator. All the navigator had to do was find the angle between it and the horizon. That gave him his latitude. Longitude is defined as degrees east or west of some fixed north-south line, such as the one through London. But in the middle of the 17th century, there was no accurate way to determine longitude. A solution in theory had been foreseen long before. Wherever the seaman is, it's quite easy to determine local noon, which is when the sun is at its highest. If somehow he were able to know at exactly the same moment the time in London, then he could calculate his longitude. Suppose he calculates his local time to be noon, whilst knowing that in London it's 2 p.m. Since the Earth rotates once in 24 hours, in 2 hours it will have turned through 1/12 of a rotation, which is 30 degrees. Since his time is ahead of London, he knows he is 30 degrees west of London.
But the problem was knowing accurate London time. This could be determined by a number of methods, such as the carrying of an accurate clock or watch on board ship. Clocks, of course, were available in the 17th century, but they were nowhere near sufficiently accurate to make this kind of work possible. In 1675, a Frenchman by the name of Le Sieur Le Saint-Pierre approached King Charles II of England with a method by which it was hoped one could find a ship's position at sea by means of the moon. The king in turn referred the method to the Royal Society of London, and they brought in the consultation of the visiting Derbyshire astronomer John Flamsteed. Flamsteed made a full critique of the method and showed indeed that it wouldn't work. This in turn was to lead to the founding of the Royal Greenwich Observatory. And John Flamsteed was warranted as the first astronomer royal to apply himself with the utmost care and diligence to the rectifying of the tables of the motions of the heavens and the places of the fixed stars, in order to find out the so much desired longitude at sea for the perfecting of the art of navigation. And what a formidable task that would be, taking up the whole of Flamsteed's long life and the making of countless thousands of astronomical observations and many, many painstaking mathematical calculations. But before Flamsteed could do any kind of map, it was necessary for him to have a 0 point of reference. This was to lead to the establishment of the Greenwich Meridian, the line that separated east from west mathematically, and from 1884 by special convention came to be agreed as the prime meridian of the world and the 0 on all of our maps. This is the octagon room at the old Royal Greenwich Observatory, designed by Christopher Wren in 1675 and the nerve centre of the Greenwich Observatory for the 40-odd years that Flamsteed was Astronomer Royal. When he first came here, Flamsteed had a rather motley collection of instruments. Some of these indeed were his own pieces, which he brought down from Derby. Others were loaned to him by various friends and fellows of the Royal Society.
In this way, Flamsteed was able to chart the positions of the fixed stars and observe the moon's path across them. But the thing that was now required to complete the longitude problem was to predict the future positions of the moon. In fact, tables of future movements of the moon would not become available until almost a century after the project began. And the production of these would depend on work carried out by Isaac Newton. It was in this manuscript that Newton provided his remarkable theoretical description of the motion of planets. Newton published this work in 1687, dedicating it in the opening pages to the Royal Society. Here was a mathematical system which unified the whole universe. Using some basic laws of motion and the concept of a gravitational force, Newton had accounted for motion both on Earth and in the heavens. In all this, the new science had played its part. The new spirit of inquiry urged by Sir Francis Bacon, nurtured by the Gresham and Wadham groups, and promoted institutionally by the Royal Society. The early years of the Royal Society had coincided, not by accident, with a blossoming of British mathematical creativity. And shortly, Britain's greatest mathematician would preside over Britain's premier scientific society. Newton's presidency enabled the Royal Society to consolidate its position. It also established his perception of the mathematical principles underlying the universe as the dominant conception in the succeeding centuries.